what are we doing now with respect to LC-MS? And as I start moving from history more towards the current state of knowledge, I like to think of this as a large target of different things that we can look at. And this is a figure from a paper that 𝗀𝗃𝗵, one of my former postdocs, put together, which I think really very nicely describes the different types of analyses that people can do for these PFASs in environmental samples. Most of us have probably done targeted LC-MS where we know exactly what we're looking for. We have authentic standards, and that is a very small subset, potentially, of the broad suite of compounds that are out there. The top assay allows us to broaden that envelope in terms of what we're looking for, and maybe we're not exactly sure how big that envelope is as compared to the targets. But one of the tools that we do a lot in our laboratory here at the Colorado School of Mines is we use high-resolution mass spectrometry. And high-resolution mass spectrometry is a way that we think is very helpful in identifying the different compounds, but also, if we don't have authentic standards, at least helping us estimate how important different polyfluorinated substances are out there in the environment. And it's debatable as to how much overlap there is between what we see via high-resolution mass spectrometry and what you see with the top assay. But we think that those envelopes are pretty complementary. We see a lot of the same things, but we get much more specificity in terms of the type of chemistry that's there. Now, if you look even more broadly, there's a lot of other compounds out there, or a lot of other tools that we think may be captured with these other types of analyses. And that's not to say that those aren't useful tools, but you have to keep in mind that they're not as typically specific as we are with high-resolution mass spectrometry, which may give you a sense of the total amount of fluorine or total amount of organic fluorine, but doesn't really always hone in exactly in on the perf and polyfluorinated alkyl substances that we're primarily concerned with. So that's why we feel the sweet spot in this is doing high-resolution mass spectrometry in our analysis. What that allows us to do is look for all of these different compounds. If you look closely, if you're an organic chemist, you like drawing different structures, you can have a lot of fun with these polyfluorinated substances. There's these perfluoroalkyl compounds that we were talking about before. All of these are polyfluorinated compounds and what we would refer to as precursors, because they can form those perfluoroalkyl acids over time. These all happen to be derived from firefighting foam, or aqueous film-forming foam, 𝗀𝗃𝗃. For those of us who speak that language, we say it really quickly sometimes, but 𝗀𝗃𝗃 is the lingo. And when we look at the broad suite of compounds, and those that are specifically derived from 𝗀𝗃𝗃, there are several hundred different compounds that are out there in these firefighting foams, or have been used in the firefighting foams. Some of them intentionally made and put into foam, some of them unintentionally. But they're all out there and all potentially present at these foam-impacted sites. So when we go out and analyze environmental samples using high-resolution mass spectrometry, we're looking for a large suite of compounds. And the tools for discovery and looking at these compounds are growing day by day. The U.S. National Institutes of Science, Standards and Technology, it now maintains a list of compounds that you can go look for if you have a high-resolution mass spectrometer, and you can look at this list, and they're adding to it as new compounds are discovered. But the point is there's hundreds, if not thousands, of compounds that are likely present at many of these sites. I should mention, by the way, that not all of these are, the thousands of compounds on the list aren't necessarily out there. We think they may be out there given the fact that these often occur in various homologous series, in other words, different chain lengths of different compounds. The PFAS world really changed in May of 2016. And that's when the U.S. Environmental Protection Agency no longer had provisional health advisories for compounds in drinking water, but had final health advisories for PFOS and PFOA, just two of the perfluoroalkyl acids that people are concerned about in drinking water. So the levels that they advised people not to drink water if they were above were 70 nanograms per liter for either PFOS or PFOA. That's not a lot. That's actually really low compared to what we typically see at impacted sites. So 70 nanograms per liter was relatively low in 2016. States throughout the US are now setting regulatory levels even lower, okay? But the point is, once we had a number, once we knew that if there were levels above this, we should be concerned, a lot more interest, a lot more public interest in this, because all of a sudden, millions of people had water that was essentially deemed unsafe to drink. And this was by EPA's action. Just to give you a sense of how small that number is and how big the problem is, if we think about the 𝗀𝗏𝗏, so again, these firefighting foams that have contained these compounds for many years, if you had just one bucket of the 1 5-gallon bucket, which is one way that it was sold here in the US, 1 5-gallon bucket of that the foam that was made by 3M, if you had one of those buckets, it had enough PFOS in it, enough perfluorooctane sulfate in it, that it would contaminate a water supply for a town of 27,000 people, the year's worth of their water. 1 5-gallon bucket. And that's assuming that the acceptable level is the 70 nanograms per liter. If you think about some places allowing only 7 or 10 or whatever, an order of magnitude lower concentrations, that 1 5-gallon bucket is enough for not a town of 27,000 people, but a town of 270,000 people. A lot of people, okay? Another way to think of it is that people often talk about parts per trillion being so many grains of salt in an Olympic-sized swimming pool. Well, I like to turn that analogy on its head. And if you had one US Olympic-sized swimming pool filled with this material, okay, filled with this firefighting foam concentrate, that would be enough PFOS to contaminate the entire US water supply, the entire US drinking water supply, for 7 years. So it's not that it would go away in 7 years. These compounds don't go away. It's 7 years worth of water. If we saved up all that water for 7 years, that Olympic-sized swimming pool would be contaminate that much water. The point is, it doesn't take much of these compounds to be contaminating water supplies, and there's a lot of it that was produced and used and released throughout the US. More importantly, it's not just a little goes a long way, but it can also impact lots of different places all throughout the US. So this is a map of places as of a few years ago that were documented to have firefighting foam releases, and places that were suspected of having firefighting foam releases. This doesn't even include volunteer fire departments, such as the local fire department here, or small towns where they might have occasionally bought a bucket of this firefighting foam and used it on local fires. So again, one bucket used by one fire department could contaminate an entire town of 27,000 people. This has potentially happened throughout the US. So we often focus on the US Department of Defense because they use this material on their firefighting foam training exercises as part of the installations, but it's not just a Department of Defense issue. Any place where they use this foam has the potential to have contaminated the groundwater, okay? And again, it doesn't take much to contaminate the water. So when I think about the complex challenges that we are going to face over the next few years, looking at this group of compounds, I think of it as a three-dimensional problem. The first is to recognize the complexity of the composition of the compounds. In other words, even though they all have a perfluoroalkyl component, there is a fair amount of complexity in terms of the different structures, particularly of the head groups. So if we were to rate PFASs as compared to other compounds, I would tend to think they're kind of up towards the top end of that list, maybe not the most complex group of compounds compared to pharmaceuticals and personal care products, but still relatively complex. And that's because of those very, sometimes very funky head groups that many of those compounds have, particularly in the firefighting foams. So that's the first dimension with respect to the complexity. It's that compositional complexity. What that leads to, though, is very unique behavior when we move out to the environment. So when we think about environmental behavior, that's where these compounds tend to differentiate themselves a little bit more. Some of them stick very strongly to solids, some of them don't. Some of them are quite mobile, others are not. Some of them bioaccumulate, others do not. The environmental behavior, some of them are volatile. Okay, the precursors are volatile, but many of them are not. And this is a level of complexity that many of our compounds, the compound classes that we traditionally have studied, they all tend to behave the same way. PCBs, yeah, there's a lot of different ones, but they all tend to be somewhat similar in terms of their environmental behavior. PFASs, you have to think about what specific compounds you're looking at. And in particular, this question of the precursors. If we're thinking about these compounds, you can't just think about PFOS. You have to think about all the different compounds that can form PFOS if you're really trying to address the issue. And same goes for any of the individual compounds, whether it's PFOS, PFHXS. You have to think about the precursors when you're considering that problem. The third dimension, which I think really makes it pretty complex, is the issue of exposure. So if we think about exposure, it is actually really complex, much more complex than for many of the other compounds. And that's where I think PFASs really do take the cake with respect to complexity. And what I mean here is that if we're looking at wildlife or humans, we can be exposed to these compounds through a variety of means. I can drink a glass of water that has these compounds in them. I can breathe in air in a carpeted environment, perhaps that the precursors are emitted from because they were used on some of the carpets. I can eat fish or eat eggs or drink milk that contain these compounds. Some of them even can get into crops, and you have to be concerned about some of them being present in food crops. So the way that these compounds go in the environment can result in all sorts of different routes of exposure to humans. And that's not even counting the fact that what you measure in me may not necessarily be what I was exposed to. If I'm exposed to a precursor, those compounds can be transformed in my body and result in a residue of something like PFOS, which will stick in my blood or stick around in my blood for a very long time. So this is what I think is one of the most important challenges when we think about this issue of PFASs moving forward. How do we address the complexity of the chemistry, the behavior, and the exposure of people and wildlife to these compounds? And that's what I really think is the question that we want to focus on moving forward. If we know these compounds are out there, we know they're extremely persistent in terms of the perfluoroalkyl acids. How important are those polyfluorinated compounds? We've primarily focused on them from the perspective of them being sources of the perfluorinated compounds. They may have their own toxicological concerns that we need to be concerned about. We simply have not studied nearly as many of them as we should. And so I do think as we're moving forward, these are the questions that we will have to be answering for the next several years. Thank you.